This opening slide sets the stage for our discussion on mineral plant optimization, focusing specifically on why particle size and shape are critical factors. Presented by Tony Escorcio, the content is part of a mineral process engineering course dated July 4, 2025. It introduces the fundamental concepts that will guide us through understanding how particle characteristics influence mineral processing efficiency and outcomes. Here we outline the structure of Chapter 1, providing a roadmap for the session. We'll begin with an introduction to the topic, followed by key objectives that define what you will learn. The summary view will help consolidate the main points. This slide helps orient you to the flow of the course and the critical areas we will cover regarding particle size and shape in mineral processing. Particle size is a cornerstone property in mineral processing, influencing nearly every stage from initial crushing to final tailings disposal. It affects separation efficiency, filtration rates, surface area for chemical reactions, and material handling. Controlling particle size is essential not only for technical performance, but also for economic efficiency, as it impacts energy consumption and process throughput. This slide emphasizes the broad and critical role particle size plays in optimizing mineral processing operations. This slide presents the first part of the course objectives, focusing on understanding the critical role of particle size and applying particle size distribution (PSD) concepts. You will learn to interpret key PSD descriptors and understand different distribution types, such as log-normal, Rosen-Ramler, and Gates-Godin-Schumann. The goal is to equip you with analytical skills to fit real-world data to models and use these for process predictions, forming a strong foundation for mineral processing professionals. Part 2 of the course objectives delves into advanced skills, particularly analyzing the impact of particle shape on various processing factors like settling behavior, flotation, filtration, equipment wear, and powder flowability. It also covers mastering particle size measurement techniques, including sieving, laser diffraction, sedimentation, and image analysis. Emphasis is placed on selecting appropriate methods, understanding their limitations, and ensuring accurate, reproducible measurements critical for process design and optimization. Continuing with Part 3, this slide focuses on process optimization and real-world applications. It reinforces the importance of analyzing particle shape effects and mastering measurement techniques tailored to material type and size range. Proper sample preparation and understanding measurement assumptions are highlighted to avoid errors. These skills are essential for applying theoretical knowledge to practical mineral processing challenges, ensuring efficient and effective plant operation. Early-stage testing during exploration and feasibility is vital for successful mineral processing plant design. Geologists and metallurgists perform comminution tests to understand ore hardness and predict energy requirements for crushing and grinding. Particle size distribution tests help determine if fine grinding is necessary and guide equipment selection and sizing. These early decisions significantly influence energy costs, equipment efficiency, and overall plant performance, underscoring the strategic importance of particle size in the initial phases. This slide focuses on crushing operations, highlighting the importance of producing particles within an optimal size range, typically 100 to 300 millimeters, to ensure efficient milling downstream. Primary crushing uses jaw and gyratory crushers to break run-of-mine rock, while secondary crushing employs cone and impact crushers for further size reduction. Maintaining a critical balance is essential. Oversized particles can choke mills, while undersized particles waste energy. Proper size control at this stage sets the foundation for efficient grinding and processing. Grinding, or comminution, is where particle size control becomes critical. Standard grinding, with sag, ball, and rod mills, targets a P80 of 75 to 100 microns, while fine grinding, with stirred ball and ISA mills, targets 10 to 30 microns for refractory ores. The balance between achieving sufficient liberation and avoiding overgrinding is key, as overgrinding wastes energy and creates problematic slimes, while undergrinding leads to poor liberation and recovery. Different ore types require tailored grinding strategies to optimize separation efficiency and energy use. Classification after grinding ensures particles are appropriately sized for efficient liberation and separation. Equipment like hydrocyclones, screens, and classifiers separate fine material ready for flotation from coarse material that returns to grinding. The critical parameter is the cut size, D80, typically 75 to 100 microns for flotation. Proper classification controls circulating load and energy consumption, prevents equipment overloading, and maintains feed consistency. Poor classification leads to inefficiencies and increased operational costs. Particle size significantly impacts separation processes such as flotation, gravity separation, leaching, and magnetic separation. Each method has an optimal particle size window. For example, flotation requires particles between 20 and 100 microns for effective bubble attachment, while gravity separation needs particles larger than 75 microns for settling. Incorrect particle sizes reduce separation efficiency, leading to lower recovery rates. Understanding these size windows is crucial for process optimization and maximizing mineral recovery. Dewatering and tailings management are heavily influenced by particle size. Fine particles settle slowly, require more flocculant, and result in longer filtration times with higher water retention in filter cakes. Coarse particles settle quickly, need less flocculant, and allow faster filtration and drainage. These factors affect tailing stability, water recovery, environmental safety, and economic outcomes. Effective particle size control in this stage is essential for sustainable and cost-effective tailings management. Transport of materials via pipelines and conveyors depends on particle size characteristics. For slurry pipelines, particles must stay suspended without causing excessive viscosity, which can increase pumping energy and risk blockages. Conveyor belts handle coarse crushed ore well, ensuring good flowability and minimal dust. Challenges include managing slurry viscosity in pipelines and preventing material flow issues and dust generation on conveyors. Proper particle size control ensures efficient, safe, and environmentally sound material transport. This slide highlights the problems caused by incorrect particle size. Particles that are too fine, 150 microns, detach from bubbles, causing poor flotation kinetics and incomplete liberation. Overgrinding creates slimes that waste energy and reduce recovery, while undergrinding results in poor liberation and lower concentrate grades. Classification errors cause high circulating loads and equipment bottlenecks. These issues have significant economic impacts, including increased energy costs. Key takeaways emphasize the strategic importance of particle size control throughout mineral processing. Optimizing particle size enhances plant performance, helps troubleshoot processing issues, and supports designing effective size management strategies. Balancing technical performance with economic objectives is crucial. Mastering particle size control is fundamental to achieving success in mineral processing, as it directly influences efficiency, recovery, energy consumption, and environmental compliance. This summary table consolidates the role of particle size at each stage of mineral processing, from crushing to tailings management. It highlights how particle size prepares feed for grinding, controls energy use, ensures optimal classification, affects separation efficiency, influences dewatering rates, impacts transport viscosity and settling, and determines tailing stability and environmental outcomes. The key insight is that particle size is a strategic control variable essential for optimizing the entire mineral processing operation. Final note: Thank you for investing in this course, the first in a comprehensive series on mineral process engineering. This series is designed with a singular purpose: to bridge the gap between theory and real-world application. In a field often clouded by excessive detail or academic abstraction, these courses aim to cut through the noise, bringing focus to what truly drives success in plant design, operation, and optimization. Each course is supported by practical tools, including ready-to-use apps, calculation templates, and engineering workflows. These are created to empower professionals, educators, and students alike to apply what they learn on the plant floor, in classrooms, or in mentoring sessions. Presentation slide decks tailored for teaching, training, or internal use are available upon request. Application workbooks, Excel and Google Sheets, and Python code for app development can also be provided to support deeper learning and implementation. If you'd like to receive any of these resources or discuss how these tools can support your work, I welcome you to get in touch. Email mpecourses@gmail.com. Thank you once again. I look forward to continuing the journey with you through the next course in the series.